Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious, the most merciful. Hello everyone, my name is Mawahib Kabbara. I am a telecommunications consultant providing consulting services to telecom operators and service providers in the Middle East in various areas of information technologies, telecom, and AI. In this presentation, I will explain what is quantization. We will get into working with real numbers versus working with integers, how the integers are easier to compute on general CPUs, and that they require less CPU cycles. We will explain the floating point format and representation, and we will perform with examples operations on floating points, such as adding two floating point numbers, for example. We will get into the advantages of quantization and the precision of quantization, and how to convert floating numbers, real numbers, into integers, int4. We will discuss the asymmetric and symmetric quantization. And finally, we conclude by discussing the known quantization algorithms used today, their characteristics, pros and cons, and which hardware they run on. In this session, I will explain quantization and its advantages, how it is used in LLMs, why it is easier to work with integers than with real numbers. Floating point representation, I will also explain how numbers are represented in 2's complement format. I will explain a number of examples to enforce the learning and to make sure that nothing remains ambiguous or assumed to be known by the audience. I will explain at what stage quantization is performed and how it affects the precision of the weight values, how to recognize quantized models by their names. The examples will include the conversion process between float number representations and integer formats such as integer 4, int4. Finally, I will briefly describe the most commonly used quantization algorithms such as GGUF, GPTQ, AWQ, EXL2, NVIDIA, NV, FP4, FP8, and then summarize all these algorithms into a nice reference table that includes the quality, best runtime, and use case of each algorithm. Let's define what quantization is. Quantization maps a continuous space, such as real numbers, into discrete values, such as integers. The sampling process of a waveform signal, where we take sample from a signal at specific time intervals, is a form of quantization. In the example below, we subdivide all the real number values between 0 and 1 into 10 equally sized intervals. The first interval includes all the real numbers between 0 and 0.1, while the second interval includes all the real values between 0.1 and 0.2, and so on and so forth. In the example below, all the real numbers between 0 and less than 0.1 maps to the first discrete values bucket, while all the values that are greater than 0.3 and less than 0.4 map to the fourth discrete values bucket. Quantization in large language models convert weights and biases from real values into integers. Let's take a look at the example below. On the left-hand side of the screen, we see the original neural network comprising an input layer, a hidden layer, and an output layer. Between the input layer and a hidden layer, there is a matrix of weights represented as real numbers, as a matrix of real numbers. And there is another matrix between the hidden layer and the output layer, also represented in the form of real number values. Now, these two matrices are not quantized yet. They are rather in floating point format, real number format. In order to quantize them, we need to convert these weights into integers. So as you can see, the matrix, the weight matrix between the input layer and the hidden layer is now made of integer numbers, while the weights and biases between the hidden layer and the output layer, this matrix is represented in the form of integer values. The question is, why do we work with integers instead of real numbers? This is due to the fact that many edge devices cannot do float number operations such as addition, subtraction, etc. on float numbers. Also, float numbers are more complex to operate on any hardware, and the representation of numbers in 2's complement format associated with integers is just simpler to deal with on local CPUs. So, using 2's complement format instead of the float number format enables the math operation of the numbers on local CPUs easily and with less CPU clock cycles. Let's take an example of adding two numbers. The first number is minus 50, the second number is plus 65. Let us deal with minus 50, which is a little bit more complex to represent in 2's complement. The procedure goes as follows. So we take the positive side of the number. We have minus 50. The positive side of this number is 50. So we represent 50 in binary format. It is 0011 0010. Then we invert every single bit. The 0 becomes a 1 and the 1 becomes a 0. That's the second step. The third step is we add a 1 and we position the 1 in the least significant side, meaning on the most right-hand side of the byte. And then we perform an addition operation on the inverted bit and the 1 that we just added. So moving from right to left, we have 1 plus 1 is equal to 0 with the carry of 1. Now the carry of 1 plus 0 is equal to 1, and so on and so forth. We end up with the result of 1100 1110. This result represents decimal minus 50. Let's now turn our attention to plus 65 in 2's complement. Because the number is positive, we don't need to do any bit inversion and we don't need to add 1 at all. All what we need to do is to represent 65 in its binary format, and it is 0, 1, 0, 0, 0, 0, 0, 1. Let's add these two numbers together now. We position the minus 50 and the 65 on top of each other, and then we add the zeros and the ones accordingly, and we end up with 0, 0, 0, 0, 1, 1, 1, 1, which corresponds to 15 decimal. Let us take a look right now at how do we represent the float 16 in the float 16 representation, and how to perform an addition in the next few slides, how to add two floating numbers together. Let us start with representing a number in float 16 first. The first step, we convert the number into its binary, and then we normalize it. Now, the number we are processing here is decimal 110, which is a positive number. We represent it in its binary format, and it is 11011110. This is binary base 2. And then we normalize it. The normalization process is about creating a fraction part from the binary representation. So the binary is 11011110, correct? So when we normalize it, we take only one number on the most left-hand side, and then everything else on the right of it becomes the fraction side of the number. So the normalization form becomes 1.101110. And we multiply it by 2 to the power 6 because we have 6 binary numbers in the fraction side of the number, 2 to the power 6. The second step, having completed step 1 already, which is the conversion to binary and normalization, in step 2, we calculate the bias component. The bias component is simply the number appearing on top of 2, which is 2 to the power. So in this case, because it's 2 to the power 6, then the exponent is 6. However, in our calculations, what we use is something called bias component. The bias component is the exponent plus 15, and we will see where the 15 comes from at a later stage. 6 plus 15 is 21. We represent this 21 in binary, and we end up with 10101. This is again base 2. Step number 3, we need to identify something called the mantissa. The mantissa is simply the fractional part of the normalized form we just did in step 1. So if we look at the normalized number format in step 1, we see 1.101110, right? So the fractional part is 101110. This is our mantissa. Now the mantissa in the float 16 is represented as 10 binary digits, not 5, not 6, not 4. So what do we do? How do we fit a 6-digit into a 10-digit format? All what we need to do is to pad it. We need to add some zeros on the most right-hand side. So in this case, the mantissa, when padded to 10 bits, becomes 10111, and then the remaining zeros all the way. In step 4, all what we need to do is to just align the sign, the exponent, and the mantissa parts we just calculated in step 1, 2, and 3. And then we end up in step 4 with the representation starting with, on the most left-hand side, it's a 0 because it's a positive number, plus the 110, right? So it is a 0. And then the exponent is the 21, which is 10101. We identified that in step 2. And then the mantissa is what we identified in step 3, and then we padded it with 4 zeros on the right-hand side. So right now, what we did is we represented 110 decimal into its floating 16 format representation. Now, there is a formula for this. It goes like the value is equal to -1 to the power sign times 1 point mantissa. So the 1 point mantissa means 1 point fraction. So we just drop, instead of the mantissa, we drop the mantissa we identified in step 3. And then we precede that with 1 point. And then we multiply everything by 2 to the exponent -15. And we return back to the exponent, which is 6. So if we just plug in these numbers in the formula, -1 to the power sign, the sign is 0, so it becomes a 1. And then we multiply that by 1 point, the fractional part, which is the mantissa, 101110, and then times 2 to the power 6, and we end up with 110. As we just saw in the previous example, we represented the decimal number 110 in floating point format that is made of 3 parts. The first part is the sign bit, which specifies whether the number is positive or negative. A sign of 1 means the number is negative, while a sign of bit of 0 means the number is positive. The second part of the format are the 5 binary bits dedicated to represent the exponent value when after adding 15 to it. So 6 plus 15 is 21, and that goes into the exponent part in the 5 bits side. Finally, the significand, this is where 10 bits are dedicated to represent the mantissa, and it's called the significand. We insert the mantissa bits in the most significant part of the significand, and we filled the remaining bits with zeros in the least significant side of the word in the significand. So in our case, we have a 6-bit mantissa, so all what you need to do is to add 4 zeros on the right-hand side, and we plug that into the significant part. Floating point representation is very helpful during model training because it enables us to magnify very small weight values or real number values by writing them in fractional format and multiplying them with the base 2 exponent. This results in enhancing the accuracy and precision of the model during the training and not ignoring small value weights in the process. I know that some of you may not be convinced that 110 is equal to 1.1011110 times 2 to the power 6. And I know why you think that way. You think that way because you believe you are working with base 10. But here we are not working with base 10, we are working with base 2, okay? Let me prove that to you. So let us convert the mantissa, which is in base 2, not in base 10. So 1.101110 base 2 is equal to 1 plus 1 over 2, or 1/2, plus 0 divided by 4 plus 1 divided by 8 plus 1 divided by 16 plus 1 divided by 32 plus 0 divided by 64. So I took everything, every bit in the fractional part, okay, and then we included the multiple of 2's incrementally as we go from left to right. And then we end up with 1.71875. Now let us multiply that by 2 to the power 6, which is 64, and we end up with 110. So this is a proof that 110 is indeed equal to 1.101110 times 2 to the power 6. As we saw in the previous example, the floating numbers operation is a bit more complex than integer calculations, okay? Adding two floats or subtracting two floats, or imagine you're working with a large model where we have thousands and maybe millions of floats. It requires a lot of operations, including calculating the sign, the exponents, the mantissa, and then adding them together. So on local CPUs, this will not run properly and requires special hardware to do it. This is why we convert them into integers, 2's complement, so that we can process them with local CPUs, especially on hardware that are not equipped to process floating number operations. We saw that operating on floating point is complex, while operating on integers is much simpler. It can be performed on local CPUs in less CPU cycles. Quantization enables us to represent models' weights and activations into an efficient format that is easier to use and to process, especially when we are dealing with thousands and millions and maybe billions of weights and activations on large models. This results into smaller models because the memory needed for integer operation is less than memory needed for floating point operations. Smaller size models are favorable, especially for those who want to run LLMs locally on their own hardware instead of renting tokens from the cloud. The inference with integers is also much faster. Quantization cannot be used during training the models because full precision is a must to train the model as accurately as possible. Quantization, however, can be done following training the model. Let's examine this into some more detail. So, during the training, full precision is required during the model training phase. This is where float 32 is used to represent the weights, the biases, and the activation values. During this training phase, fine-grained precision is essential. Real values must be used to calculate gradients and to tune the weight values. To speed up the training process, Google has come up with the float 16 format, which uses float 16 at half the precision instead of float 32, yet still achieve very good precision results. After the training, however, LLM quantization can be done for inference. Inference consists of a forward propagation, which can sustain some minor loss precision. Integers, such as int4 in this stage, can be used during inference. Some models available today can successfully run inference in integer precision as low as int8 or int4 or even int1 bit, as we've seen from Microsoft lately. Quantization, in summary, is best done right after the model training and before deployment. This is known in the industry as post-training quantization, or PTQ. We can't expect all models to be quantized, especially those models running on the cloud. For example, Meta and DeepSeek published their large language models in their original floating point format. The open source community, however, and other companies such as Onslaught quantize these models and then release them as quantized versions. We can easily recognize the quantized version by their suffixes in their names. So when we see, for example, in the name something like GGUF, AWQ, GPTQ in the name, this will indicate that this model is quantized. Qwen publishes quantized versions of their LLM models. There are models called quantization-aware training. These are models that are trained with extra precision to compensate for post-training quantization losses. The important question to ask here is, how do we ensure that the quantized model operates as good as the original model, and that the precision is maintained, or even if degraded very marginally, not to have any serious impact on the prediction of the model? In the following slides, we will explain converting the floating point numbers into integers and how this will affect the precision. Let's take a look at the 4-bit integer precision format referred to as INT4. In AI, INT4 is commonly used in quantized models where weights and activations are converted to 4-bit precision integer format to optimize inference or prediction tasks. INT4 provides several benefits. First of all, INT4 is a good balance between storage size, range, memory usage, and performance compared to higher precision formats such as INT8 or floating point 32, FP32. The second advantage is the performance improvement. For example, it has been reported that 59% performance increase in inference throughput compared to INT8 on NVIDIA GPU. Finally, there is a memory efficiency advantage because INT4 reduces the memory and the bandwidth requirements, thus enabling the execution of large language models on GPU hardware. INT4 has a drawback related to accuracy, but it's not very serious. We've seen reports that the accuracy loss is about 1% in some cases, or even less. Let's explain an example where we convert a real number such as 23.5678 into its corresponding INT4 format. With quantization, instead of storing the real number 23.5678 directly into memory, what we store instead are the following. First of all, we store a small 4-bit integer and a scaling factor referred to as S. S let us approximately reconstruct the original value of the number when we do dequantization. So, for signed 4-bit integers, the bit width here, n, is equal to 4 because we are doing INT4. The number of distinct value for INT4 is 2 to the power 4, which is 16 values. The signed range is given by the formula, so the signed range Q refers to or belongs to an interval 2 to the power n minus 1 as a minimum, and the maximum is 2 to the power n minus 1, and then the result minus 1. So in our case, a Q belongs to the interval -8 all the way to 7. And as we can see here, it is asymmetrical because we have 8 values on the negative side, and we have 7 values on the positive side, and we have 0 in the middle. So the representable integer codes are -8, -7, -6, all the way to 0, and then all the way to 6, all the way to 7. There are 2 naming conventions that are used, a Qmin and Qmax. Qmin refers to the most negative number, which is -8, and Qmax refers to the most positive number, which is 7. On the right-hand side, I created this table here to show you the 4-bit representation for each value. So the value 0 has 4 zeros. The value of 1 has 1 in the least significant bit, and then zeros in the most significant bits, and so on and so forth, all the way to -8, which is represented as 1, 0, 0, 0. Again, this is INT4 format. Let's discuss how we map real numbers into quantized integers using linear quantization. In this example, we will use signed integer 4 that has 16 integer values starting at -8, -7, all the way to 6 and 7. On the slide below, we use one marker for each quantized integer value. These markers are depicted by small vertical lines aligned with the quantized levels -8, -7, -6, all the way to 7. In total, there are 16 markers to depict the 16 quantized levels. It takes one step, also called one score, to jump from quantized level -8 to quantized level -7, and it takes 8 jumps from level -8 to reach quantized level 0. It also takes 15 jumps, i.e. 15 steps, to move from level -8 all the way to level 7. The diagram below shows clearly the 16 quantized levels as well as the 15 steps from level -8 all the way to level 7. Note that every change in one scale in the real world moves us exactly one level in the int4 world. A step means the movement from one quantized value to the next. Note that the real number range has a minimum value and a maximum value. In asymmetric quantization, the real numbers range has a minimum value that falls perfectly on level -8 and a maximum value that falls perfectly at quantized level 7. It might seem logical for the audience to wonder why we are talking about 15 steps instead of 16 equal intervals or 16 bins as shown in the diagram below. Let's clarify that for a minute. The 16 equal sized bins is like dividing a pizza into 16 equal slices. This determines the size of the pizza slice. While this is not what we are trying to figure out here. Instead, what we are trying to do here is to determine the quantized level for each real number. This process is based on the number of steps needed to determine the quantized integer 4 level for each real number. The round function is also used to round the value of the real number when divided by the score to the nearest integer, meaning the nearest quantized level, not the bin number. The scale formula below determines how the scale is calculated for asymmetric quantization based on 16 quantized levels. And we see that 15 represents the number of steps needed to go from quantized level -8 to reach quantized level 7. You can count them actually. There are 15 steps, and this is the maximum. This number 15, you will see it in the formula. When calculating the score, you see division by 15. This is where the 15 comes from. As an exercise, let us quantize real numbers in the range between -1 and 1. The minimum for this range is equal to -1, and this falls exactly on quantized level -8, while the maximum is 1 and falls exactly on quantized level 7. Let us calculate the scale for this range. The scale is given by the formula, the maximum value minus the minimum value, and the result is divided by 15. So in this case, it is 2/15 or 0.1333. We also provided the calculation for the bin width, although it is not important and not used in AI for quantization actually. We only included it here to show that the bin width value is less than the scale value. The table below shows how the real numbers are mapped to the various quantization levels. We will explain this in more details in the following slides. Now let's do a detailed example. Let us quantize a real number range between -20 and 35. Now, although this range is quite large and does not give us good precision, but for the sake of illustrating how quantization is calculated on the real number range, we are using these extreme values. -20 is the minimum range value here, while 35 is the maximum range in this interval. As discussed earlier, -20 is really the minimum and lands exactly on the integer -8. This is quantization level -8. While the value 35 is the maximum value for the range and lands exactly on quantization integer level 7. So let's do the calculation here. Let us calculate the scale first. So the scale is the total range. The total range here is the width of the interval. So it's 35 minus 20, or 35 plus 20. So it is 55, and we divide that by 15 steps. We end up with the scale equal to 3.666. Now, to determine the quantization level for any real number value, call it x in this case. So we take that value, which is x, or weight or anything, and we subtract from it the minimum value for the range, and then we divide it by the scale, which is 3.666 here. The results is not going to be an exact quantization level number. Instead, it's going to be like a real number. So we round it to the nearest integer level. So Q here is the quantized level, is equal to round x minus min divided by the scale. And then we add to the result the integer minimum, which is -8 in this case. So minimum is equal to -8. This is the lowest quantization level because we're starting from -8 all the way to 7. Okay, for the sake of example, let us see where the values 34 and 17 ends up. Let's take 34 first. So for the value 34, if we try to determine the distance from the minimum, it is 34 minus the minimum, which is -20. So it is 54. We take this value and then we divide it by 3.666, which is the scale. We end up with 14.727. So we have 14.727 steps. We round it to the nearest integer. It is 15. When we round 14.727, we end up with 15. And then we apply the offset, how far we are from the minimum quantization level, which is -8. So 15 minus 8 is equal to 7. So what this means here is that the value 34 is going to be quantized into level 7. Okay? Let's do another example. Mapping the value 17. Again, we calculate the distance from the minimum. So it is 17 minus -20. So 17 plus 20 is equal to 37. We divide it by the scale, which is 3.666. We end up with 10.09. We round it to the nearest integer. It is 10. And then we apply the offset, how far it is from the minimum. So 10 minus 8 is 2. What this means is that the number 17 will map to quantization level 2. There are two primary ways to perform the mapping of real numbers into quantized levels. There is the symmetric quantization and there is the asymmetric quantization, and we will discuss this in more details. Let's compare the asymmetric versus symmetric quantization and look at the subtle differences that confuse a lot of people, especially around why do we divide by 15, why do we divide by 7, where do the minimum land, where do the maximum land on the quantization level, etc. Let's start with the asymmetric quantization. In the asymmetric quantization, where we divide by 15, in this case, the asymmetric quantization maps the entire real number range, or the float range, as we call it, onto the entire integer range. This integer range for int 14 can be anywhere from 0 to 15 or -8 to 7. It doesn't matter. In both cases, it is 16 codes either way, so 16 levels. The endpoints are pinned exactly. So for the minimum range, this aligns with quantization level 0 if we are using 0 to 15, while the maximum value lands at quantization level 15, again, when we're using the interval 0 to 15. So going from code 0 all the way to code 15 is 15 steps. Okay? There are 16 levels we explained earlier and 15 gaps or 15 steps between them. And it takes 15 steps to go from quantization level 0 all the way to quantization level 15. This stride must cover the full span, maximum minus minimum. So if we look at the score is max minus min divided by 15. And we gave an example on that earlier. This is just the distance divided by the number of steps, and then we get the scale. This is an ordinary linear interpretation across the 16 grid point or the 16 levels we talked about. Let's switch now to the symmetric quantization. In symmetric quantization, instead of dividing by 15, we divide by 7. Let's explain why. In symmetric quantization, we have a symmetrical interval starting from -7 all the way to 7 with a 0 point exactly at 0, at the quantization level 0. We still have the same alignment, so where the real value is equal to 0, this lands at quantization level 0, while the maximum, and we see this in absolute value because the value here, W or X or whatever, can be negative or positive, but in either case, it aligns to either 7 or -7 on both sides of the spectrum of the interval. So 0 lands exactly on code 0, and that's the entire reason to go symmetric with no 0 point. A lot of quantization algorithms prefer this because it's very symmetrical from -7 all the way to 7 with 0 in the middle. It just makes things easier. And most of the time this is implemented in software because the hardware by default uses -8 to 7. So this is adjusted in software to use symmetric instead of asymmetric, or to use the quantization level -7 to 7 instead of -8 to 7. So going from code 0 to code 7 is 7 steps, covering only half the span on the positive side of things, not the full max minimum range. So S here, the score, is equal to the maximum value of X, which can be positive or negative, as we mentioned. And we divide that by 7. Why? Because it takes 7 steps from quantization level 0 to reach quantization level 7. Also, the same way, it takes 7 steps to go in the opposite direction, to go from level 0 all the way to level -7. Okay? So I hope this explains the differences, the subtle differences between asymmetric and symmetric quantization. Now, most of the quantization algorithms, as I mentioned, they prefer the symmetric quantization because of the symmetry and the 0 point aligning exactly at point 0. This is just simpler and it makes the quantization unbiased. While with the asymmetric, we have -8 on the negative side and 7 on the positive side, which makes the quantization a little bit unbiased. Let's talk a little bit more about symmetric signed quantization. We can take the weights as an example, just to make it more realistic and more practical. In symmetric quantization, okay, let's talk about the hardware first. The hardware on the computer uses native signed integer format in 2's complement format, starting from -8 all the way to 7. While in symmetric quantization, it uses a manual chosen signed artificial integer range between -7 and 7. This is designed to be mathematically symmetric around 0. We mentioned that many LLMs such as GPTQ, AWQ, and so on, with 0 point exactly at point 0, they use symmetric signed quantization. And we talk about the alignment where the minimum aligns with -7 while the maximum aligns with 0 for the negative side of the interval. And for the positive side of the interval 0 to 7, the minimum aligns with 0 while the maximum aligns with level 7. So, to map a continuous range of real numbers such as, let's talk about a range between -2.5 to 3.1 into 15 discrete levels of signed INT4, we used the linear quantization as explained before. And we're giving the formula here on the right-hand side. So the formula is we round the value, the real number value, we divide that by the scale, and then we round the results to the nearest integer. And we calculate the scale as the maximum absolute value of x, because as we mentioned, this formula applies to the positive side of the interval or the negative side of the interval, meaning between 0 and 7 or -7 to 0, same thing. We divide the real number range into 14 steps, okay? Now remember these numbers, okay? 14 steps for symmetric, while we have 15 steps for asymmetric. It will come in the next few slides. So we divide the real number range into 14 steps or 14 scores. And then we assign every value in the particular bin, which is like the chunk of the real number range. We map that into the quantized levels. So as you can see in the picture below, if you count the number of vertical lines in red, you will see 15 values, which are from -7 all the way to 7 and 0 in the middle. And then you see 14 steps to go from the minimum all the way to the maximum. Now, depending on the bins or the values that are, for example, that happens to fall between a certain value and another value, it would be mapped to a particular integer level. And you see the integer level quantization bins there. You see them filled with some numbers. These are the real numbers that are mapped into the corresponding quantization levels. Let's have another look at the asymmetric or affine quantization with int4 signed. But in this case, instead of using the quantization level 0 all the way to 15, we are using the signed version, which is -8 all the way to 7. We also do the same thing. So the formula here in this case, it's the same formula, but instead of the 0 point being equal to 0, in this case, the 0 point is equal to -8. And we always calculate the scale in the same way. Now let's talk about asymmetric, also called affine quantization. In this example, we are going to use integer 4 unsigned, meaning starting with 0 all the way to 15. We are not starting with quantization level -8 all the way to 7. Instead, we are starting with the quantization level 0 all the way to quantization level 15. This is important, okay? So to map a continuous range of real numbers like -2.5 to 3.1 into the 16 discrete levels of signed int4, we also use the linear quantization. We divide the real number range into 15 scales or 15 scores. Now, note that with asymmetric quantization, we use a 0 point, okay, in contrast to the asymmetric where we do not have a 0 point, because always the real number value of 0 aligns or falls exactly on the 0 level quantization or level quantization 0. But with asymmetric, this 0 point can shift, okay? So with asymmetric quantization, we use the 0 point to shift the range, and we will see how this is calculated. We apply the formula Q equal round the x, the value, the real number value, we divide that by the scale, and then we add to it the 0 point. In this case, it is 0, because we're starting from zero quantization level or level quantization level 0. So z here in this case is equal to 0. And the scale we always calculate it as a maximum minus a minimum divided by 15. Okay, this is how things work with the quantization level 0 to 15. So again, if you count the number of steps, you will find 15 steps, and you will find 16 vertical lines depicting the 16 quantization levels we're talking about between 0 and 15. Now let's walk through an example of converting the real number 23.657 1 into int4 format. Before we can map continuous value to one of the 16 int4 levels, we need to decide which slice of real number space those 16 bucket or 16 quantization levels cover. That slice is the calibration range. We call it the calibration range, and it is typically expressed, as always, with the minimum and a maximum for asymmetric quantization, or with a single maximum value, maximum absolute value rather, for symmetric quantization, and we covered that in the previous slides. To perform quantization, an LLM deployment calculates a calibration range per group of 32 up to 128 values, real number values. These real number values can represent weight or can represent something else. Depending on whether we are using unsigned int4 or signed int4, the 16 levels can be all positive, for example, from 0 to 15, or some of them are negative between -8 to 0, and the other is 0 to 7 positive. In either case, the calibration range decides what the 16 possible values of int4 mean. Calculating a calibration range per group of 32 up to 128 real number values or weights helps to reduce the errors. In contrast, if we don't do that, and if we instead calculate the calibration range for the entire range, or the entire tensor as we call it, this would otherwise result in large errors in the prediction. The calibration range has a minimum value and a maximum value. In this example, and for convenience and easy math, we have chosen the minimum to be 0 and the maximum to be 32. We explained that there are two ways for quantization. There is the asymmetric quantization and there is the symmetric quantization. Let us start with the asymmetric or affine quantization, and let's call this method A. And in this example, we are going to use unsigned int4, meaning the quantization level starts at 0 all the way to 15. As we mentioned earlier, the asymmetric quantization uses both a scale and a 0 point, where the 0 point can shift, unlike the symmetric quantization where the 0 point is always at quantization level equal to 0. So the first thing we do is we compute the scale. We talked about this a million times. We look at the range, the maximum minus the minimum divided by 15. So 32 minus 0 divided by 15 is equal to 2.13333. This is the scale. And then we compute the 0 point. So the 0 point here in this case is equal to 0 because we're starting from 0 all the way to 15. Now, why a 0 point? It's the int4 code that represents real value 0. When the range minimum is 0, the 0 point is naturally 0. But for the range like -10 to 22, the 0 point shifts the mapping, so the integer 0 no longer has to sit at the low end of the integer range. Moving on, still with method A, which is the asymmetric affine quantization. So we calculated the scale, and now let's continue. We need to quantize. So quantize meaning finding the quantization level that the real number x will be mapped to. So Q is equal to rounding the real number x after dividing it by a scale. So scale is 2.133, right? So we take the x divided by the scale, and then we round the number, and we add the 0 point. The 0 point in this case is 0. So because we are trying to map the number 23.6571 to the quantization level, we divide that by the scale, which is 2.1333, and we get an answer equal to 11. Now, we need to clamp this number that we get for Q between the interval 0 and 15. And fortunately, 11 is already in the range. 11 is already between 0 and 15. So there is no clipping needed in this case. Now, if we are to dequantize this, meaning going in the reverse direction, so the value, the dequantization value is equal to the quantization level minus the 0 point, and we multiply that by the scale. So it is 11 times 2.1333 equal 23.67. Now I want you to compare these two numbers. So x hat, which is the dequantized value, is equal to 23.467, while the number that we were trying to quantize is 23.6571. The difference between them is the error. So we call this the quantization error, and it is equal to 0.19, or about 0.8 relative error. Let's quantize the same number, 23.6571, but with symmetric quantization this time. And let's call this method B. So as we explained earlier, with symmetric quantization, the quantization levels start from -7 all the way to 0 all the way to 7. So the first step is always the same. We compute the scale. So the scale is equal to the absolute value of the maximum and divide that by 7. So it is 32, which is the maximum, divided by 7, and we end up with the scale equal to 4.5714. And then we quantize. The formula is Q equal round X, which is the value 23.6571, divided by the scale, which is something we just calculated, that is 4.5714, and we end up with 5. Now I want you to notice that the scale here with the symmetric quantization is larger. Okay? And notice that with symmetric quantization, there is no 0 point, because the 0 point always aligns with 0 quantization level. And then after we obtain the quantization level, which is 5, we try to see if we need to clamp it. So 5 falls between -8 all the way, between -7 and 7. So there is no need to clamp it. Now, if we are to dequantize it, the formula x hat is equal to the quantization level multiplied by the scale. So it is 5 times 4.5714 equal to 22.857. Now, I want you to look at the original number, which is 23.6571, and then the dequantization value we obtained, which is 22.857. Obviously, there is an error. There is a difference between the two numbers equal to 0.8. This 0.8 represents 3.4% relative error. Obviously, it's larger here. Having done the quantization using two methods, the asymmetric quantization and the symmetric quantization, let us compare the two methods and the results we obtained. So on the left-hand side, we see the asymmetric or the affine quantization. The range is 0.15, which is the unsigned, all positive. And it does use a scale and a 0 point. The 0 point can shift, as explained earlier. We obtain the quantization level equal to 11, and then when we dequantized it, we received an answer of 23.467, or we obtained a value in the calculation equal 23.467. The error was almost equal to 0.19 or 0.8%. This is best for skewed, non-zero centered data. In contrast, let's take a look on the right-hand side of the screen representing the results we obtained from the symmetric quantization. So the range is -7 all the way to 7. And then it uses a scale only, no 0 point, because 0 point always falls on 0 quantization level. We obtain Q equal to 5. And then after we dequantized, we obtained x hat equal to 22.857. By subtracting the dequantized real number value from the original real number value, we obtain an error of 0.8, which is 3.4%. This is simpler math and cheaper to compute per group, but obviously we received higher error with the symmetric quantization. This is a summary slide depicting what we can take away from the various quantization we have done so far. So we always start by picking a range. We took an example where we took the range between 0 and 32. From that, we calculated the scale. And then depending whether we are using symmetric quantization or asymmetric quantization, we decide whether there is a 0 point or not. Then we take the original real number we're trying to quantize, we divide it by the scale we just calculated, and then we round it to the nearest integer. And then we decide whether there is a need to clamp it if it falls outside the range or within the range. And then we store it as int4 proper quantization level. So we talked about quantization and how to convert from real numbers into the various quantization levels. And we discussed the various techniques such as the asymmetric quantization and the symmetric quantization, and how to calculate the scale and how to decide in which quantization level each real number falls. So we discussed all of that. Now let us talk about the most famous quantization algorithms that everybody is using nowadays. The first thing I want to talk about is the GGUF with the K quantization, which is not an algorithm itself. Rather, it is a file format wrapping several quantization schemes. The K variant with GGUF allocates bits per block intelligently. For example, the attention layer might get 6 bits, while the feed-forward layers might get 4 bits. This is why GGUF achieves better quality per bit than naive uniform quantization. Llama C++, known as Llama CPP, uses the GGUF quantization naming scheme and uses the quantization symbol Q as well as K for the quantization method and M for the size. Let us decode the naming convention used in GGUF so that we understand what the Q means, what the K means, and what the M means. So Q stands for quantization bit width, meaning how each weight or how each real number is stored using 4 bits instead of the original 16 or 32 bits as FP16 or FP32. So instead of using FP16 or FP32 when we quantize, we are using 4-bit instead of the 16 or the 32-bit. This is the primary level for compression. For example, with FP16, the size of the file is around 140 gigabyte. This shrinks divided by 4 into roughly something like 35 to 40 gigabyte when we use 4-bit quantization. So the size is divided by 4. Other common values you will see things like Q2, Q3, Q5, Q6, or Q8. Again, this is the number of bits used for the quantization. The lower the number is, the smaller the file is, the more the quality loss. K stands for the quantization scheme, meaning which quantization scheme we are using. So here we're talking about the algorithm of the quantization. So K-quant group weights into superblocks. So what the K-quants does, it groups the weights or groups the real numbers into superblocks. This superblock can have a size of 32 or 128 or even more, and then use a more sophisticated per block scaling approach. So for each block, it assigns a scaling approach for each block, because each block is different, and some weights are more interesting, more important than others. So it assigns the bits more intelligently based on the importance of the weights or the importance of the real numbers and how they affect the output. The result is that we can noticeably achieve better quality retention than legacy quantization, which uses the same bit width across the board. Now, in the naming convention, when you see something like Q4_0 and you don't see any K in the naming convention, what this means is that the file in the LLM is using the older or the simpler method. This is something that you want to avoid because it's using old techniques and does not give you the kind of quantization efficiency and quality that you expect. M, finally, stands for the size of the quantization scheme. So M comes in 3 variants, either small or medium or large. The S, M, and L, they control how many layers or tensors. Tensors, by the way, are multidimensional arrays that serve as the fundamental data structure for organizing and manipulating data. They can represent various types of data such as images, videos, sound, and relationships among words and concepts. Tensors are crucial for performing operations in neural network and other machine learning algorithms. So, the M size variant with the K quantization scheme, they control how many layers or tensors get the higher precision treatment within the mixed precision scheme. So again, we're talking about mixed precision schemes here. We talked about K, right? So the K quants don't quantize every layer identically. Not all the layers get the same quantization. We talked about this when we discussed K. Some sensitive tensors, like attention output, get kept at slightly higher precision. M is the common sweet spot, which provides better quality than S for a modest size increase without the huge size hit of the large size. Here is a quick reference table for the GGUF file names that specifies the Q, K, and M values in the various models. The first quantization is Q2K. This indicates that 2 bits are used instead of 4 bits for quantization. Obviously, this will lead to heavy quality loss, although it may be acceptable sometimes for very large models where the file size can be a problem even with the 4-bit quantization. In such situations, there can be a compromise on the quality in favor of the model file size. With Q3 uses 3 bits for quantization and achieves a quality improvement over the 2-bit version, but is still considered a major quality degradation. With Q4, things start to get better. This is where we can achieve good balance between file size name and good quality with the quantization of 4 bits. With Q5, the quality even gets better and provides a quality that is very close to the original quality and can support larger models. With Q6, this is almost lossless. The quality is even better. And still, despite, it's good quality, it's still meaningfully smaller than the FP16. With FP16, floating point 16, the file size is huge still. But with Q6, you get very good quality, and still the file size is a fraction of the size of the FP16. With Q8, this is essentially lossless. There are no losses. Yet, we're still achieving the benefits of compression. So the file size is reduced. Now, a quick reminder, the K-quants group the weights or the real numbers into superblocks and use a per block scaling approach, assigning bits more intelligently based on which real numbers or which weight, for example, matter more. The S, M, and L control how many layers or tensors get the higher precision treatment when we're using the mixed precision scheme. GPTQ, which stands for Generative Pre-trained Transformer Quantization, this is a post-training quantization algorithm, meaning the models are pre-trained first, and then a quantization algorithm is applied on the trained model. GPTQ is one of the first practical 4-bit methods. It uses a calibration data set, and it quantizes the weights or the real numbers layer by layer to minimize the increase in loss. It's still solid, but has been replaced by new or modern quantization such as AWQ. GPTQ specifically minimizes the construction error during the second-order Hessian-based information. It does not just round each weight independently. Instead, it accounts of how errors in one weight can affect other weights in the same layer, then corrects that. GPTQ typically quantizes into 4 bits, sometimes in 3 bits or in 8 bits, with weights stored as int4, alongside with the per group scaling factor, which we discussed earlier, the scaling factor, remember that? GPTQ runs almost exclusively on GPU, unlike GGUF, which can run on the CPU or GPU with flexibility. GPTQ, it assumes the CUDA acceleration from NVIDIA. Where is GPTQ used? Historically, it has been the dominant format on Hugging Face for GPU-only local reference and is served via Auto GPTQ and is also called as XLAMA version 2. AWQ is yet another quantization algorithm. It stands for Activation-Aware Weight Quantization, which rather than treating all weights equally, it observes the activations during the calibration phase to identify which weights stands out, which weights are salient. It protects those weights and at a higher precision. On the NVIDIA hardware, AWQ has overtaken GPTQ. Its activation-aware scaling cuts the int4 quantization penalty from 4.57 to 1.17 perplexity. It outperforms GPTQ on reasoning at the same bit width because it's a newer model, so that's logical. A 2026 Qwen3 with 32 billion parameter benchmark showed AWQ cutting the GPU memory by 42% with only 1.2% accuracy drop. EXL2 is another quantization algorithm. It's kind of proprietary because it's used in XLAMA version 2. So EXL2 is XLAMA version 2 on quantization format. What's interesting about this quantization format is that it allows fractional average bit rates. For example, 4.65 bits per weight as opposed to a whole integer bits like we've seen in the previous algorithms. So EXL2, it allows the usage of fractional average bit rates with per layer variable precision. How it's different from GPTQ is that it allows variable bit rates per layer. It gives more bits to sensitive layers and fewer to robust ones, and also allows the fractional average bit rates. EXL2 generally considered to squeeze out better quality per gigabyte than GPTQ at the same file size because of that per layer flexibility. NVFP4 or NVIDIA Floating Point 4 is receiving a lot of investment and attention for the Blackwell chips with the Blackwell tensor cores. So NVFP4 is a 4-bit floating point built for the Blackwell tensor cores. It retains a more dynamic range than fixed int4 formats. It does support 8-bit floating point, FP8, and int4, and FP4 through a single unified toolkit from NVIDIA called Model Optimizer. This requires a two-step process where the quantization is done first offline using the model OPT with quantization FP8 or targeting the NVFP4 specifically. Then the resulting checkpoint is compiled into the TensorRT LLM engine. We can run the NVFP4 KV cache together with the FP8 weight or activation quantization. FP8 or floating point 8. This is a GPU native 8-bit floating number, real number, achieving near baseline quality with much faster throughput than the 4-bit methods. FP8 is a common production default when memory is not a problem, where file size is not an issue. Finally, here is a summary table capturing everything we discussed so far when it comes to the various quantization algorithms. I just want to focus on a couple of algorithms that stand out. Basically, the AWQ, the activation aware, salient weight protection with INT4, and it can run with auto AWQ, VLLM, or TensorRT LLM. It achieves the quality when compared to the floating point 16 around 97 to 99%, and this is considered the best in class at the 4-bit. The other one I want to mention is the NVFP4, which is optimized for the Blackwell chips, especially the GB10 used in the NVIDIA DGX Spark, for example, and the OEM versions of the same hardware. This provides a quality of around 92 to 98% depending on the task, and it can run on TensorRT LLM via the model optimizer, as we mentioned earlier. Finally, the FP8. This is the best kind of quantization, which is very similar to the original quality without quantization. So it's like near the baseline, and the accuracy is around 99%. It is latency sensitive production and can achieve KV cache compression, and it can run on TensorRT LLM with VLLM. It uses 8-bit floats and GPU native. I hope that this explanation was useful, and feel free to use this set of the slide deck. You can use it as a reference in the future when you want to check about the various quantization models. This is the end of our presentation. We covered a lot of material on the mathematics behind the quantization, how quantization works, and the various quantization algorithms used today. I hope the video was useful and that it provided the necessary information to reinforce your learning. I appreciate your constructive feedback. Please drop your comments in the comments section below. Thank you, and see you in the next video.